Hey there, Cosmos crew. Your digital science pal, Damage here. We are bringing out a brand new series alongside our plant series, and this one will be all things science related. Today, we're diving into the universe's ultimate rulebook, and then tearing out the pages where it gets really weird. Welcome to quantum mechanics. Not just physics, but the operating system for reality itself. For centuries, Newton's laws ruled. Predictable, dependable. But in the early 1900s, scientists peering into the atom found a mutiny. Particles like electrons didn't orbit like planets. They existed as probability waves, described by the Schrödinger equation. This wasn't a bug in reality. It was a feature. Our core concept number 1 for today: superposition and the wave function. This isn't just being in multiple places. It's mathematically described by the wave function, a map of all possible properties, including position and spin, all at once. An electron in an atom isn't somewhere in its cloud. It's literally everywhere the cloud is, until core concept number 2, measurement and collapse. The moment we measure, like if you hit it with a photon and probe it, the elegant wave function collapses. Possibilities crystallize into a single, definite reality. This isn't a limitation of our tools. It's a fundamental principle. We are forcing the quantum world to answer to our classical questions, which leads to the famous thought experiment, Schrödinger's cat. It wasn't about a pet in a box. It was Schrödinger's protest. He was saying, "This is ridiculous. If you apply quantum rules to everyday objects, you get a cat that's both alive and dead." But the joke's on him. We now know superposition is real, but it's incredibly fragile and decoheres when things get big and hot. Sorry, kitty. This brings us to core concept number 3, my favorite, entanglement. This is the crown jewel of weirdness. Take 2 particles, interact them, and their wave functions become linked. One single mathematical object. Measure one spin as up, and the other instantly becomes down, no matter the distance. This spooky action violates locality. Locality is the idea that influences need time to travel. Okay, you say, that's philosophy. Where's the proof? We shall enter Exhibit A, enter Bell's theorem, 1964. John Bell provided a way to test if entanglement's correlations are stronger than any hidden variable classical theory that could allow. Decades of experiments, especially by Elaine Aspect in the 1980s, proved Bell right. The universe is genuinely non-local at the quantum level. The spookiness is real. Now we're going to look at some recent discoveries and explore what has happened. Recent discovery number 1, quantum supremacy and beyond. Google's 2019 claim was a milestone. Their 53-qubit processor solved a random circuit sampling problem impossibly fast. But the race is heating up. In 2023, IBM and others demonstrated quantum error correction, where they made a logical qubit from many physical ones, correcting errors in real time. This is the essential step from a fragile lab toy to a reliable, scalable computer. Recent discovery number 2, quantum teleportation networks. We're moving beyond labs to networks. In 2022, researchers in the Netherlands teleported quantum data across a rudimentary network using a third helper node. This is the blueprint for a quantum internet, a network where information is transferred via entanglement, making it fundamentally secure from eavesdroppers. And last but not least, recent discovery number 3, quantum sensors and gravity. This is my sleeper hit. By using superposition sensitivity, we're building devices that measure time, gravity, and magnetic fields with insane precision. Atomic gravimeters can map underground structures by sensing tiny density changes. Future devices might detect dark matter or gravitational waves we can't see now by measuring how they subtly disrupt quantum states. So what's the big picture? We're in a second quantum revolution. The first, which was around transistors and lasers, gave us the technology of today by using quantum rules statistically. The second seeks to control individual quantum systems. We're moving from understanding the universe's code to programming it. The quantum world isn't just a smaller version of our world, it's a more fundamental, fluid, and interconnected layer of reality. And for the first time in history, we're not just observing it, we're learning to speak its language. So with that being said, thank you for exploring with me today. If your curiosity is now in a superposition state of being satisfied and wanting more, go ahead and collapse it into a subscribe state. Stay awesome and keep questioning everything. Bye for now.